The next supporting project was, as Tim mentioned in the original presentation, in 2003, 4, and 5, when we wanted to decide which earthquake really is main shock, aftershock, we had to decide based on the reading information, some judgmental, some any form, non-uniform decision. Then Katie examined the so-called aftershock versus main shock, and in fact, in order to avoid any misunderstanding with the other seismological community, she called it class 1, class 2, just to avoid. And she's going to present the new classification. Katie.
Thank you. Okay, my name is Katie Waddell, and I'm a member of the Geosciences Department at PG&E, and I'm sorry if I'm a little hard to understand today, but this is the voice I woke up with, so we're going to go with it. Today I'm going to be talking about how we classify main shocks and aftershocks in the NGA West 2 database. And this is a really important topic because over the last 20 years, the developers of the ground motion prediction equations have been noticing that the median ground motion from aftershocks is systematically lower than the median ground motion from main shocks by about 20 to 40% at short spectral periods. And so what we need to do is classify these aftershocks so that each developer can make the decision, do they want to include the aftershocks in their model or and account for the differences in the ground motions, or do they want to exclude the aftershocks and only look at main shocks? So in this presentation, first what I want to do is provide an overview of what each developer, how they treated the aftershocks in the 2008 models. And then I'm going to show how we're classifying the aftershocks in the 2012 models. And then the remainder of the time I'll spend showing, presenting the new terminology that we've developed and explaining really what those terms mean. So in 2008, although each developer started with the same database of about 3,500 recordings from 173 earthquakes, the database that they ultimately put into the regression had many differences. And one of the key differences is in the treatment of aftershocks. So in this table here, I'm showing in the top row the total number of earthquakes that went into the regressions for each of the 5 NGA models. And this is the total number of earthquakes. This is main shocks and aftershocks in the top row. And in the bottom row, I'm showing the number of aftershocks that went into the regressions for each of these models. And what you'll notice is the 2 models with the largest data sets, the Abrahamson and Silva model and the Chu and Young's model, included about 45, 46 aftershocks in the regression, and they had a larger data set. The other model that included aftershocks is the Idris model, but the overall number of earthquakes is lower because this model is limited to the rock site condition. The Boren-Atkinson model and the Campbell and Bezornia model did not include aftershocks, and they had a smaller database. And Tim mentioned this morning, but I want to reiterate that a qualitative approach was used to classify the earthquakes in 2008. And the aftershocks were independently classified by each developer team. In 2012, we now have a much larger database. The number of earthquakes is increased by about a factor of 3.5, and the number of recordings is increased by a factor of about 5.5. And now we're taking a more quantitative approach to classifying the aftershocks in our models. So our aftershocks, as Yusuf said, we're calling class 2 events. They're classified using a methodology that's similar to the Gardner-Knopf declustering algorithm. But there are some key differences, and I'll explain those later on. But the point I want to make here is, and I said it before, it's up to each, once this classification is made, it's really up to each developer team to decide how to incorporate this information into the models. The figure I show here shows the distribution of earthquakes in our database with respect to magnitude on the y-axis and distance on the x-axis. The blue data points are the main shocks, and the red data points are the aftershocks in the data set. And I'm showing this figure to show that the aftershocks are well distributed both in magnitude and distance, and to also point out a difference between the 2008 database. The aftershocks in the 2008 database were dominated by Chi-Chi aftershocks, so that when the developers included these into their models, it had some large differences. So these are the new terms that we are introducing. And the remainder of the talk will be focused on really looking at each of these terms. I should mention now, and there are two words we try very hard not to say, and I've been saying them a lot, but we try hard not to mention the word main shock, and we try not to mention the term aftershock. And the reason we avoid these terms is not because we take any issue with them, but they have broad definitions, and they already have specific meanings in the seismological and earth science community. And we're not adopting those definitions, and we're not trying to redefine them either. So in order to be unambiguous and avoid confusion, we've created our new terms with specific definitions to hopefully clearly communicate exactly what we're talking about. So Class 1 earthquakes are those classically defined main shocks, foreshocks, triggered events, and aftershocks that occur off of the Class 1 or off of the main shock rupture plane, or outside the time window that's appropriate for aftershocks. Our Class 2 events are aftershocks that occur on the rupture plane of the main shock, the Class 1 main shock, or are very close to it. And what is close is going to be up to each of the developer teams to decide, and I'll show some pictures to explain what I mean in a moment. And with these two terms, we have a new distance metric. This is the centroid joiner bore distance metric. So in NGA 1, there's the joiner bore distance. And what the joiner bore rupture distance is the distance between your site and the surface projection of your earthquake. It's just that closest horizontal distance. Our centroid joiner bore distance is now the distance between the centroid of the surface projection of that potential Class 2 aftershock and the closest distance to the surface projection of the main shock rupture plane. And I have a picture, so if this is not completely clear, don't worry. So I'll start with the centroid joiner bore distance metric. So in this figure, let's see if I can get the mouse to work. This yellow star represents the epicenter of the main shock. This long red line is the surface projection of the rupture plane, and the dotted line, this dotted line is the surface projection of the rupture plane, and the red line is the surface projection of the top of the rupture plane. So then we have three potential aftershock, Class 2 aftershocks in this figure here. There's one here, represented by the epicenter is this small orange star. There's another one here and another one here. And the symbols, the plus signs with the circles around them, those are the centroids of the aftershock, the Class 2 aftershock rupture planes. So when you see this centroid inside the surface projection of the main shock, we define that to have a centroid joiner bore distance of 0. And what we assume in our data set is anything within an appropriate time window with this centroid joiner bore distance of 0 is a Class 2 aftershock. And it's up to the developers then to decide how far away you can get from this surface projection of the main shock before you expect ground motions that are more characteristic of Class 1 earthquakes. And I'll get back to that in a second. But the distance between then this centroid here and the main shock rupture plane defines that CRJ distance for earthquakes that are off of this main shock rupture plane. So we developed this distance metric to help us explore a hypothesis, which was that earthquakes that rupture on this surface projection of the main shock rupture plane should have lower stress drops than earthquakes that happen off of this rupture plane or far from it. And because there's a correlation between stress drop and ground motions, it follows that ground motions then should be lower for earthquakes that re-rupture this main shock rupture plane. And you could expect that as you increase your distance from this main shock rupture plane, your ground motions could increase to look more like main shock ground motions. And so, like I said, it's kind of up to the NGA developers, each developer team, to figure out how large of a CRJ distance they want to use in their models for that threshold. So now hopefully we have a more clear idea of what the CRJ distance metric is. I want to talk a little bit about the methodology we use to classify these Class 2 earthquakes in our database. So we started with the Gardner-Knopf declustering algorithm. And so the Gardner-Knopf methodology uses a time window and a distance window that is scaled by the magnitude of that main shock. So the red points in this figure show the Gardner-Knopf time window, and the blue points show the Gardner-Knopf distance window, and the lines that connect them show our fit to their model. So for example, if you had a magnitude 6 earthquake, anything within about 500 days and 50 to 60 kilometers of that main shock would be considered an aftershock based on the Gardner-Knopf methodology. We have adopted the time window without modification in the NGA West 2 model. And I want to mention that in doing this, we have ignored potential effects of fault healing. So there's an idea that after an earthquake ruptures, the fault plane can stiffen over time or heal. And so if there's a large effect due to healing, it may potentially cause, we may potentially want to modify the time window, and this is a topic for potential future study. The distance window, we did not adopt the distance window. And the reason we didn't adopt this distance window is because it's a radial distance metric. So for a magnitude 6 earthquake, to use our previous example, I can find the pointer, anything within 50 to 60 kilometers of that epicenter could be considered a class 2 earthquake. But what really matters for ground motion is not how close you are to the epicenter, it's how close you are to the fault plane. And if you're 50 kilometers to 60 kilometers away from the epicenter, you could potentially be very far away from that rupture plane. And the other extreme, in that case, you would get a class 2 earthquake that might or probably should be considered a class 1 earthquake. And on the other extreme, say you have a long rupture plane. If your hypocenter or epicenter is at one end of the rupture plane, and you have aftershocks at the other end of the rupture plane that are on the rupture plane, because you're using a radial distance window that may not extend out to the end of the rupture plane, you could misclassify, you would get a class 1 earthquake for something that should be a class 2. So we're not using the distance window. Instead, we're using that CRJ distance metric that I previously described. And it's up to then the developers what threshold they want to use for that CRJ cutoff. So this is just to show an example. This is the Coalinga sequence here. And the large yellow plane here is the main shock, the class 1 main shock. And here's that epicenter here. And we have 4 earthquakes that are within that rupture plane. So they are class 2 when we have a CRJB distance threshold of 0 kilometers. And then the earthquakes outside of that rupture plane are considered class 1, given that we're using a 0 kilometer threshold. If we increase that threshold to 2 kilometers, we grab this earthquake. And if we increase the distance threshold to 5 kilometers, now we have all of these earthquakes considered as class 2 in the model. So I was going to conclude. How's the time, Yusuf? Are we? Okay, so I was going to conclude with an example of how this is being applied in the Abrahamson and Silva model. But since Norm is next, is this in your presentation, Norm? Okay, well.
So we cut it from his time.
Okay. Do you want to start with my figure, or should I wrap it up, Norm? Okay, so what I'm showing here, these circles here are event terms from the potential class 2 earthquakes in the database. And this 0 line here would represent the main shock model. So basically anything with a negative event term would be an earthquake that had lower ground motions than what would be predicted just using a model with no aftershocks in it. And so what we see is within about 5 kilometers, over 5 kilometers, we have a systematic lowering of the ground motions. And by about 15 kilometers, There are very few data points. This was in a preliminary version of the model, but within about 15 kilometers, the ground motions are then increasing to something that's more characteristic of a Class 1 type earthquake. So what the Abrahamson and Silva model is doing then is applying a constant term here from 0 to 5 kilometers. Have you changed that? Okay. And then there's a taper so that by 15 kilometers, basically that aftershock effect goes away. So, thank you.
Very good.
And,
thank you very much, Katie. This is the issue of aftershock. I'm very positive that in the next couple of years we are going to dig into that. One reason was Darfield earthquake, which was followed by Christchurch earthquake in New Zealand, created lots of practical engineering issues. Questions for Katie, classification of aftershock, main shock. Jerry.
Have you attempted to reclassify some aftershocks as following an earlier aftershock rather than a main shock?
No, we haven't. It's all based on the main shock, the largest event in the cluster.
Oh, then you're not familiar with the well-known theorem that big shocks have aftershocks to follow them that frighten. Aftershocks have aftershocks, and so ad infinitum.
This sounds like the ETOS model, right? So, I'll have...
That's okay. Just wait. All right, Zia.
Just wanted to ask about the following model you showed on.
Which file is this?
Oh, okay. I don't know exactly. I can find that information for you, but they were all within the time windows predicted by the Gardner-Knopf algorithm defined. So
They are not class 1 then?
That's okay.
that's correct. They're all class 2.
Even those ones who would go outside of the distance?
They're all class 2, well, depending on what you choose as your threshold CRJB distance. So if you were only looking over a CRJB distance of 0, only those aftershocks or class 2 events which occur on the surface projection of the main class 1, the main shock rupture plane, would be class 2 events. If you extend that threshold to 2 kilometers, then you're looking a little bit further away from this rupture plane, so you grab this event. But then if you extend your distance to 5 kilometers, they're all considered class 2 earthquakes.
Are both conditions need to be satisfied?
Yes, both, yes, that's correct.
Great.
I'm sorry.
Great. Thank you very much. I appreciate that, Katie.